Some of the hardest problems in the world exist far above the planet. Our job? To launch the smartest solutions, to protect our satellites, clean up our clutter, to propel breakthroughs in propulsion, to learn more about our place in the universe, to outpace emerging threats. Every day, the Aerospace Corporation uses the latest technologies to ensure our nation's safety and leadership in space.
Welcome to the Space Policy Show. We have Bill Ailor on our show today. He's going to be talking about hazards of reentry disposal of satellites from large constellations. We are so excited to have Bill here. He is a technical fellow at the Aerospace Corporation Center for Orbital and Reentry Debris. He has been with our company since 1974, and he's worked in this area since then. So we are very lucky to have him. Thanks for being here, Bill. Just a few quick things. So normally we would ask you to join the chat, have questions, but we did have some technical difficulties. The Vimeo platform was down for about 30 minutes earlier, so we decided to go ahead and just record this. So thank you for those who tuned in. We really appreciate it, and thank you for your patience. As a reminder, we're here every Tuesday and Thursday at 1 p.m. Eastern. Also, you can find out more about us by visiting aerospace.org/policy. We've got papers, we've got all of our events listed there. You can also click to watch past episodes. We will also be posting this episode there. And without further ado, we'd like to kick it over to Bill. Bill, thanks for being here.
Thank you, Rebecca. I've been at the company since the middle 1970s, and over that period of time, basically up to say 2004-ish or so, most of the reentries that we looked at were individual spacecraft, one-of-a-kind type things, where something would be coming down occasionally. We might see, say, 50 or 100 satellites a year, maybe less. And some of those would be very large, some would be very small. So this particular topic interested me because we're talking about lots of satellites of the same type being put into orbit. And the question was, what would that mean relative to reentry hazards? So that's what I'll be talking about today. So first, I'll just describe something about reentry breakup. I'll give you a little bit of information on what the government policies are regarding reentry hazards at the present time. I'll talk to you about a year 2000 case, 20 years ago, that actually was the first to raise this issue of constellation hazards and what the cumulative hazard might be. And then I'll show you some details in some of the constellations that are being put up. And we'll talk about the risk to people and on the ground and in aircraft from possible reentries of these. So next chart, please. Okay, just want to make you aware that they're leaving out a lot of details in this. And if you would like to see more details, there's a paper that's available from our Center for Space Policy and Strategy. Next chart. Okay, this chart basically gives you an overview of what a reentry looks like. The spacecraft on the left side of the screen basically is coming in as it looked in space. As it starts getting deeper in the atmosphere, it starts to heat up due to the interaction with the atmosphere. It loads increase. The aluminum surfaces and aluminum structures and so forth will begin to melt. Some of the early things will fall off that were part of the external things exposed to that heat. Sooner or later, you see we've seen cases where there are big major breakups of a spacecraft, and the internal material will get spread out and released into the airstream, and each one of those objects then will fly and will get its own heating. But typically these objects, whatever survives those reentries, will basically just sort of fall from about 100,000 feet, more or less straight down, and make it to the ground. You'll notice on that figure there's an 18-kilometer vertical piece on the far left of the ground hazard, and that's basically where aircraft fly. We'll talk more about that later. You can also notice the size of these footprints. Sometimes they can be quite long. This is about 2,000 kilometers long and maybe 70 kilometers wide. And that might be the case for a large spacecraft. And these are what I'm talking about here is an orbit decay type reentry. If you direct something in, could be a little shorter. So next chart, please. Okay, so the U.S. government orbital debris mitigation standard practices, which were just updated, really focus on orbital debris mitigation. And that's what do we do to keep the debris population of things in orbit from getting too high. And so as part of that, you can dispose of satellites that are in low Earth orbits into the atmosphere, just bring them in, and most people think everything burns up. And so we're all good there. And basically what these regulations say that the risk of human casualty from surviving components with impact kinetic energies greater than 15 joules should be less than 1 in 10,000. That 1 in 10,000 number is a key piece to this discussion. And basically, if you have a spacecraft that exceeds that hazard, that means that you would need to deorbit it into an ocean area or something like that. And the way to think about that 1 in 10,000 is that if you were to enter that same spacecraft 10,000 times, you would expect to see one casualty somewhere on our planet. Next chart.
Bill, I have a question for you. What does design for demise mean?
Okay, design for demise is one of the things that can be used to sort of diminish the hazard, shall we say, for reentering objects. Typically, what you could do is rather than use steel and components or these high melting point materials, you can use more aluminum, for example, which will melt away fairly quickly on a reentry. You can do other things with the structure, so that basically is when you design a spacecraft, build in those features so that when you're actually reentering it into the atmosphere, it'll come apart and create fewer hazardous fragments. That's really what that means. Okay, next chart. So basically, this goes on to say, the government standard practices also define a large constellation. This is the first time it's been included in the standard practices, and it basically says that a large constellation now is any constellation that has more than 100 satellites in it. And even for those, it says, if you look at the bottom, it basically says that direct reentry, which means drive it into the sphere. You basically target a spacecraft so that it comes in a particular place. That is the preferred mission disposal option. And then it also says you should limit the cumulative reentry hazard, but it doesn't limit it in any fashion. It just says you should try to limit that business. So there really are no specific requirements for casualty risk for reentry of a constellation yet. Next chart. So basically, I did find a reference for national test ranges. This is RCC 321-17, and it's got a note in there that says that the collective risk for the general public should not exceed a casualty expectation of 3 times 10 to the minus 6, or that's 3 in 1,000 on an annual basis. And so the idea there is that if you understand what the hazard is going to be in a year, then you can sort of have a limit on it, although it has not been applied to satellite reentries yet. Next chart. Okay, so basically that case I mentioned, which is a 2000 case, this was when the Iridium constellation, the Iridium was going basically bankrupt. And so there was a concern that they would be reentering 74 satellites, all in a very short time. And these were all in low Earth orbits, and they would all be brought down and then orbit decay down. Each satellite had a dry mass of about 560 kilograms. And NASA predicted this. I wanted to use something where it's been documented what the prediction estimates would be. Was about that about 30% of the dry mass, that's the amount of the mass of a spacecraft without all the liquids and gases in it, would be. So 30% of the dry mass would survive. And the casualty expectation for a single Iridium satellite then was 5 times 10 to the minus 5, which is below that hazard limit for a single satellite of 1 in 10,000. That's a very important point. So basically each satellite that would come down from that constellation would meet that requirement. However, if the cumulative hazard that NASA predicted for this was 1 in 250 roughly, and that would mean it was 4 times 10 to the minus 3, much higher than just for a single satellite. And since they were all coming down in a short time, that hazard could be manifest over a short time. That did propose an issue of liability for the United States, and fortunately DoD action prevented that bankruptcy action. Next chart.
Bill, I have a question for you.
Oh, sure.
How many of the old Iridium satellites have re-entered?
That's an interesting question. And we've had, just for example, we had about 40 Iridium satellites come down in 2018 alone. And so there were a number of satellites that came down that year. They are gradually bringing them down, at a fairly good clip as they put the new replacement, the Iridium Next satellites up. And so, and since that time, that fragment we saw on the first earlier charts is the only one that's been recovered to my knowledge. And we've had no casualties. Next chart. Okay, so here's a list of these possible new constellations. Now, this study was done in late 2018 and 2019 when these were the satellites that were being proposed. Of course, there have been some changes, and we can expect that, but the intent of the study was really to look at what the possibilities might be, given the fact that you could have, say, 4,425 satellites up there, or 7,518, or 112 of different masses and things, and really trying to do a study so we can get a feel for what this really means to have these large satellites coming down, or large constellations coming down. A key, excuse me, a key parameter there is the satellite lifetime. And so basically the satellites now, back in the old days, they'd want them to last forever. But now we're cutting the lifetime down so that you can keep refreshing and replenishing these satellites with new technology. And you see the relatively short lifetimes. So in my study, I need to make some assumptions about how many are going to be coming down on a yearly basis, or we can dump them all in at one time. And I assume that, for example, on that first constellation there, SpaceX, there'd be a satellite lifetime of 6 years. And I interpreted that to mean that they would be bringing in 1/6 of that constellation every year. And so that's how I used it in this study. And so the satellite mass of those satellites was estimated to be around 390 kilograms. And the inclination also has an effect, and I'll talk more about that. Next chart.
Bill, I have a question for you.
Oh, sure.
There are a lot of CubeSats going into orbit. Do they present a reentry hazard?
You're right. Another thing we're seeing relatively recently, that means since 2000, are lots of CubeSat reentries, or CubeSats going up, which means a lot of them are coming down. The general rule of thumb on a spacecraft reentry is that anywhere from 10 to 40% of the dry mass will survive and impact the ground. And for a CubeSat that weighs a few kilograms, that's not going to be much of a hazard, and certainly would not trigger any kind of the ground hazard limits. And so at present, we don't worry about those, and I didn't discuss them in this paper.
Great,
okay.
Thank you.
Mm-hmm, sure. Okay, so some of the basic assumptions I made were that we had to guess on the constellation satellite properties. That's the mass and mission lifetime. We don't have official information on that, but these are sort of what was known at the time. The satellite designs were based on publicly available information in late 2018, and they're being believed representative. We're assuming these constellations are already up there. And so I'm using the year 2030. So we've got all of these things up in their constellations. They're operating on, just as they would for normal operations in steady state. And then we use best guesses toward basics like numbers per plane, orbit inclinations and things. And then assumed disposal strategy for constellation satellites, which means that they're all going to come in randomly. In some case, they may not choose to do that, but right now I assume they are all coming in randomly, which means they can land anywhere on the planet. Next chart. Okay, so let's talk to people about the risk to people on the ground. Next chart. Okay, so first, many people think that things don't survive reentry, but I've shown you a few pictures here that show you that things do. That picture on the bottom left there is the debris from the Iridium satellite that was recovered in 2018. That, as I mentioned earlier, was about the only piece of debris that's been found, as far as I know, from the reentry of any Iridium satellite. But the other ones you can see are things that we have brought back, basically, and aerospace and the Air Force will bring these things back and do research on them to understand how these things broke apart, what kind of environment did they see? How can we improve our models so we can do a better job of predicting it? That one on the top left, I'll talk about later. But that big one on the right is about 250 kilograms, about 600 pounds or so, and it landed next to a farmer's house in Texas. He wasn't too pleased by that. And then you can see these other two are basically wrapped with some kind of a filament, and that material then acts as, if you will, almost a heat shield that will have some of these tanks and so forth come down and survive very nicely. Next chart.
Bill, I have another question before you move on.
Oh,
so
sure.
How do you find re-entered debris?
Well, basically, that's a good question. And back in the late 90s, when we first set up our Center for Orbital and Reentry Debris Studies, we set up a web page that people could contact us if they found something or saw something that looked like it might be some reentry debris, or if they saw a reentry and they said, that looks like a reentry. What is it? And so we were looking also for news reports, and some of these times we'd see something like those two on the top, or something that we saw in a news report, and we actually brought them back and did some work on those. The ones in the middle, I think those were news reports as well. They come down all over the world, and we've got some stuff from Saudi Arabia and other places, Mongolia, for example, where we've been contacted by news media. And the one we saw on the bottom left there is just something that was a police photo. So we saw that went in the area where it came down. So we get material, stuff like that, and if it's something that deals with an Air Force stage, for example, then we can try to bring it back. And we've worked with SpaceX on one of their stages as well, and that's been quite nice. Next chart. Okay, so for this study, this is a first order estimate. So I can't do a lot of detail, a really fine estimate on this, because these constellations really aren't fully configured yet, and they're certainly not in space. So it's assuming steady state operations, and I had to make an assumption, like I talked about, of what steady state operations means from the disposal perspective. And so as I said, I look at that from the number of satellites reentering per year, and you can see if we get a satellite lifetime of 5 years, it means 1/5 is coming down, all of these are by orbit decay. And also, one thing you can do is have people sheltered if you know where it's coming down, that makes sense to do. If you don't know where people are going to be, it's doesn't really do much for you. And then debris can fall anywhere along the ground track of an orbit, and we can talk more about that. Next chart. Okay, so I mentioned casualty expectation a few times, and that's defined here, or give you what's important to it. Size and mass of the debris that survives reentry is a key piece, of course, because the component itself will define the flight trajectory and how fast it hits the ground. The impact energy is derived from that, and if it exceeds that 15 joule number, it's called a hazardous object. The casual area is the area of interaction with an average human, and right now an average human is defined as 1 foot radius. And the population density is a number of people per unit area for the impact region. And if we know where that is, again, you can do a good job on defining what the hazard would be. But for a random reentry, you basically look at the population that's that's covered by the orbit itself, and so basically it's based on the inclination. It's the population on Earth between plus and minus, say, 50 degrees for a 50-degree inclined orbit, and the total population casualty expectation is the product of the population density and the total casualty area. Next chart. Okay. So another thing we don't know about these spacecraft is what's the design going to look like? What are the components? And so for this one, I was looking for a spacecraft, not a tank, not a structure like a propellant tank on a stage, but something that would be included within a spacecraft. And I used the iridium example, the iridium case as a source for information on that. And so I assumed a similar mix of propellant tanks, thrusters, electronics, batteries, and reaction wheels, and so forth. And then I assumed that basically the satellite, the same mass of an iridium satellite, 560 kilograms, and in the same orbit inclination, I'll describe that in a minute, would have the same casualty area as a Iridium satellite that re-entered that year. And so that's a place to start. And again, one would do a better job if he knew specifics, but I think in the first order is probably not too bad an assumption. Next chart. This chart just shows that the casualty expectation as a function of orbit inclination. And again, since this is population based, so you would expect that around the area, like say 35 degrees inclination, if an orbit is going over that plus or minus 35 degrees on the Earth in latitude, then it would go over a lot of people, Los Angeles, a number of big cities are in there. And so that would give you a peak, and it does. And so this is what you use, but it really does show you that orbit inclination for a constellation or an re-entering object is very important in computing what the overall hazard is going to be. Next chart. Now, this is the risk to people on the ground. And here, in this case, so basically what we're looking at is the mass per satellite, the number of reentries of each of those satellites. And again, that's about one, it's basically the number of satellites in the constellation divided by the orbit lifetime. And then the EC for each satellite reentry is set by the mass of the spacecraft. And the casualty expectation per year in 2030 is what you see there. And so basically it says, at the bottom there, it says the total casualty expectation per year in 2030, if every constellation is up there and re-entering in the way I said it would, you'd have a casualty of about one person for every 3 years or so. And that means, again, one person somewhere on the ground, somewhere on the planet would be injured or potentially hit fatally every 3 years. And so basically what that tells us is it is important to understand how these things are going to come down and what their casualty expectation is. Next chart.
Bill, before you move on,
yep.
How many reentries happen per year now, approximately?
Well, let's see. Again, I'll use 2018 as a reference, but I was looking at that. It's about 140 total reentries that year. And if you look at the mass, about 80 of those had a mass of larger than about 100 kilograms. And that means that there are a lot of them that were much smaller. And this is showing that we're beginning to see a number of these small satellites coming down. And I might mention that about 40 of those spacecraft that came in, which are higher than 100 kilograms, were from the Iridium constellation, as I mentioned earlier. So, and again, it was not uncommon to see some fairly large rocket stages come in. The largest one that year was about 7,500 kilograms. So that's quite a largest object coming in. And again, it's very rare to even see a reentry these days, and much more rare to actually find any debris on the ground. Next chart. This is it. Okay, so summary for the ground hazards. For the three constellations that we looked at, each satellite reentry exceeded that 1 × 10⁻⁴ number, and so that would mean that those operators should really consider direct reentry disposal of their spacecraft at the end of life, rather than orbit decay as an option. The cumulative risks for 3 constellations were greater than 3 × 10⁻⁵, which, if you remember, that Range Commanders Council limit was the 3 × 10⁻⁵, which meant that if that was a regulation, they would exceed it. And then if all constellations are operating, again, it's about 0.3 or 3 every 10 years. Next chart. So let's talk about aircraft. So next chart. Okay, so again, this is the picture I showed earlier, and at this point, we're worried about what falls through that little square that little area on the bottom that shows that it's called the ground footprint. But what survives reentry and falls through that? And is there information out there that we can use to understand or to make a rough guess as to what might happen for something like that? And so I'll talk a little bit about that now. Next chart. Okay, so let's talk about debris that's potentially lethal to an aircraft, and there's some references on that are available. First, potentially lethal debris is defined as something that could cause loss of life or necessitate emergency response by the crew. And things that could happen be fragment penetration of an aircraft structure or a windshield, and ingestion by an engine. And then there's other information that says that what commercial aircraft were vulnerable to, like a 1 gram cube of stainless steel or a 9 gram cube of stainless steel that could actually penetrate a fuselage. And so that gives us something to work with. Basically, it says that ballistic coefficients that we would look at, a ballistic coefficient is looking at basically the basic characteristic of object that's falling, would range this area of 50 to 100 kilograms per square meter. And so we can find some data that will help us, that can help us with understanding how this might work. Next chart. Okay, and then I thought this was an interesting point here. That woman on the left is Lottie Williams. She is outside of Tulsa. She was out running in the morning. She was brushed on the shoulder by that piece of debris. It didn't hurt her, but we managed to get a copy of, had a little piece of that sent back. We examined it and found out it was from a reentry rocket stage. And this is what the reference at the bottom says about that. One of the worst objects an engine can ingest is a piece of cloth, i.e. a shop rag, and thin plastic sheets and quilted pads. Some guys can cause trouble too. So this would kind of cause something where it might bother an engine, requiring some action by the crew to deal with that. But it's an example that even some of these things, like this one, which brushed her on the shoulder, didn't hurt her, potentially could cause issue if it were to get ingested by an aircraft. Next chart. Okay, so fortunately, one of our employees, Dr. Russ Patera, did a really nice paper on the risk to commercial aircraft from reentering space debris some years ago. And he basically looked at commercial aircraft flying domestic flights within the United States, flights leaving the U.S. for international destinations, and flights coming in from international points of origin. And he looked at a range of aircraft types, as you can see there, and got information on each aircraft type as to number of passengers, wingspan, and so forth, and was able to develop some charts that we can use to assess what that risk might be. Next chart. Okay, now this chart is an interesting one. I was looking for something that actually said, okay, fine, what actually survives a reentry that we can basically say has been documented? And this was a set of tests, or a test that was done back in early in the 70s sometime, and something called a vehicle atmospheric survivability test. Radar actually observed debris falling after a reentry and breakup of a pretty large spacecraft, 5,300 kilograms. Was not a launch stage, and that's important. Launch stages, as I said, that will have a few large pieces that come down typically, but not a whole lot of little things. Spacecraft is characterized by internal components such as electronics boxes and batteries and so forth that will spread out and come down. So it's a different animal. And this basically said that the number, you can see what's here, that threshold then is defined, is using the ballistic coefficient numbers I mentioned earlier that were for stainless steel and aluminum to kind of define a threshold for damage to an aircraft. And you can see there are a lot of objects higher above that particular threshold that potentially could have caused trouble with it had an aircraft flown through that. The other thing to notice about that chart is that the distance from heel to toe on that particular thing was 800 kilometers. And you can see that this debris was spread out over a fairly long range. And so that's an example of how far this stuff can come down, and gives you a feeling for what we're dealing with here. Next chart. And then also just another example, and this was unique in the fact that there was a major effort to recover debris objects. This was the Space Shuttle Columbia accident. Over 80,000 objects were recovered, and the casualty expectation for commercial aircraft at that time was about 0.3. So that could have been a problem. Fortunately, there was no impacts that we're aware of. And then, so basically what I assume for this study is it will have about 300 objects per 800 kilograms of satellite mass, which was based on something that we had done before. Next chart. And so just to show you here, just as with the ground hazard, the aircraft hazard for aircraft would be a function of inclination of the orbit. And basically, Dr. Patera used the population in 2006, a distribution of population in these latitude bands as an indicator of what the aircraft population would be. So another assumption. But since this was in 2006, and only included stuff coming into and flying in, coming into and leaving the United States, potentially aircraft flying. There were a lot more flying, or could be a lot more flying if you bring in the international flights as well. Next chart. And this is casualty expectation per debris object for these same aircraft. And you can see the aircraft types considered again. And so what he was looking at here was what was the, if an object was to hit an aircraft, what would be the casualty expectation? And so again, if you have to hit an aircraft to have a casualty, which is a key piece of this. And so the casualty expectation, if you see like 0.6 casualty expectation, you can't have anything on as a casualty unless you've actually hit an aircraft, which could be much more serious. Next chart. And this shows what the risk to aircraft might be. And so in this case, we have a number of satellites, same reentry type of thing coming up. You can see that the number of hazardous fragments that are would be created, by my assumption at least, in that fourth column, and the number of hazardous fragments per year can be quite large in sometimes, and that kind of indicates that as these things come down, you're going to be spreading out a lot of debris. That's over 400,000 fragments of debris that would be coming down that year if everything was re-entering as I assumed it would. And probably a striking an aircraft in total would be like 2 in 1,000. And so that means every 500 years or so, you might strike an aircraft. But if you did, then the cumulative casualty expectation per year could be would be like 0.6. But again, that really means that you have to hit an aircraft before that can happen. Next chart.
Bill, have there been any known impacts of debris on commercial aircraft?
Very good question. And that's something I've been looking for a long time. The only reference I found about that was a newspaper article that talked about a commercial flight in China that was flying at altitude, 30,000 feet. And the pilot noticed a flashing metallic object just before it struck the windshield of the aircraft. And it caused an emergency. It actually broke the outer screen of the windshield. And he actually did an emergency response to that and landed the aircraft. So that's the only one I'm aware of. And if anyone knows of that, knows of any more, I'd be pleased to know about those. Next chart. I got this in conclusions. We can go back up to that one if you don't mind. Okay, perfect. Okay, so it basically says in conclusions that the reentry hazard certainly can be something to be thinking about for ground impacts. And so that means that's looking at the cumulative hazard should be something that we consider over time. And the risk to aircraft posed by small debris surviving a reentry might also be a major issue that we need to be thinking about. And I just want to emphasize again that right now we don't have good data on what kind of small debris survives a reentry. And as we propose these design for demise schemes, we would need to verify them in some fashion. And I want to just conclude there that says that casualties could be significantly higher if there are different disposal strategies. For example, if a Constellation was going to be re-entering all of its spacecraft in a short time or double that number of used, the casualty expectation would be weighted by that. So again, it does make a difference on what the strategy is. Next chart. And so as far as recommendations go, I would encourage that spacecraft operators consider direct re-entry into a safe area to minimize hazards to people on the ground and in aircraft. That satellite should be designed to reduce that survival hazardous fragments during reentry. That should be just a best practice, I would think. And we need to conduct some flight tests to verify this design for demise techniques that may be proposed. And so I would encourage us to be doing that type of thing. And then another approach, of course, would be if you know of some large objects coming down that might pose a significant hazard, you potentially could warn them out of those areas. So that would be something to be thinking about as well if there are big objects coming in. And I think that's it. Happy to take any questions.
Great. Thank you so much, Bill, for being here and for your patience with our technical difficulties we had earlier. I have one last question. Do you think there should be a cumulative re-entry hazard limit for constellations?
I actually think over the long term, that is definitely something we should be thinking about. I don't think right now we have enough information to make a smart estimate of what that should be. And for a way for a satellite operator or designer to estimate what it should be. So I would think in combination with doing some reentry tests, we would ultimately may want to do that. Looking forward in time, we may see a lot more objects up there than we're seeing now, and these constellations may be larger or smaller. I do think that we should be considering some kind of a limit like that, yes.
Thanks, Bill. And one last question. What would you leave our viewers with today? One key takeaway that you want them to walk away from this talk with?
Well, first, a little understanding of the reentry breakup process. Maybe a second thing would be to look for things on the ground that look like they've been damaged by thermal means, pieces of debris that look like those I showed or something else like that, because we collect these things all the time. And then finally, this is an area where we have been blessed for a number of years with only a few reentry hazards to deal with. But we're looking at a situation where we've got a lot more. We need some better data, I think, to make better estimates.
Okay, great. Thank you so much, Bill. Was there anything else you wanted to share before we wrap up today?
No, I think that's good.
Thank you again so much for being here. We're really appreciative that you took the time. Also, for the viewers who are watching this, again, we appreciate your taking the time to join us, and we apologize for the difficulties earlier. Again, you know where to find us. We're at aerospace.org/policy. And our next episode is Space Grows Faster When It's Safe. Safety and Sustainability with Joseph Kohler and George Neild. Thank you again. Don't forget to sign up for our alerts. And with that, it's a wrap. Thanks so much.
Thank you.